Even though the ingredients are simple and the techniques to make it haven't changed for centuries, when you make bread, you're applying a large variety of scientific concepts. To begin, it's important to explain the most ubiquitous ingredient in bread, flour. Flour's molecular makeup can be given credit for a lot that is appealing about bread. Flour contains a number of different proteins, namely glutenin and gliadin. These proteins, in addition to starches inside the endosperm of a seed, are the sources of energy for the germination of different plants, such as wheat or barley, each of which are used to bake bread. These proteins have an interesting structure and reaction with each other that allows dough to be stretchy and bread to be light and tough. Flour is made up of these proteins and starch from the crushed up endosperm of the seed. When you bake with it, these proteins that are present within it are what makes everything stick together. Flour's proteins don't form bonds while it's dry. Otherwise, flour wouldn't be the powdery texture that it is. Adding water primes the proteins to form bonds that are present in the final product. These proteins absorb the water, allowing it greater mobility and therefore a better ability to make bonds. When you knead the bread, you're now kneading together tons of primed proteins, causing them to stick to each other, forming disulfide bonds and hydrogen bonds, among others. The glutenin and gliadin within the flour stick together, with the small round gliadin proteins dispersing themselves within the long strands of glutenin. These complex proteins, called gluten, then stick to each other. After enough kneading, the dough is no longer sticky because of the extent to which the gluten have interacted. This gluten is the reason why you've probably been warned not to stir pancake batter too much before cooking it. Ideally, pancakes are light and fluffy, and if the gluten has been agitated too much, it results in a tougher pancake due to all the bonds that are present. However, in bread, this gluten is important because it works in tandem with another ingredient, yeast. Yeast is a small, single-celled fungi which wakes up when you warm it and give it something to eat. Yeast acts as leavening in the bread dough by consuming the sugars available in the flour and turning it into CO2 and other byproducts. When the yeast go to work releasing the CO2, it gets caught on a web of gluten that was formed by kneading the dough, causing the dough to rise and giving the bread a lighter texture. This is why some breads made with gluten-free flour, even if they do contain yeast, will end up being flat or tough. Without the gluten, they don't have any proteins to capture the CO2 that's produced by the yeast. On the other end of the spectrum, there are also doughs which contain a whole lot of protein that results in a whole lot more gluten, such as the whole wheat flour which I'm using in the video. This inclusion adds a lot more proteins, which results in a tougher dough, which explains why the whole wheat variations of crackers or other treats may seem less appealing. This doesn't even begin to explain the extreme variety of different breads or what adding different ingredients does to the final product. Things like sourdough breads and sandwich breads have extremely different processes which go into the final product. Given all these factors and the science behind them, when you make bread, you're really partaking in a little bit of chemistry or biology.